So using the trig identities to simplify a trig expression is one use of trig identities. Another use is to verify new trig identities. So what we mean by verifying a trig identity is to show that an equation has left side equal to the right side. And since we're unsure at the beginning of the verification process whether the left side actually does equal the right side, we need to approach this as though they're not equal. And so because of that, some of the rules of algebra don't apply. So what do we mean by this? Well, since we are unsure at the beginning if the left is actually equal to the right, we can only multiply by 1 on each side of an equation. So normally if you have an equation that you're solving, let's say it's this, we can divide both sides by 3 and we're good. X is equal to 5 because we know at the very beginning 3x must be equal to 15. However, when we're verifying a trig identity, we don't yet know that the left side is equal to the right side. So we can't just do the same thing on the left as we do to the right as we would when we're solving an algebraic equation. So specifically, no cross multiplying. It's very tempting to want to do this. Similarly, no moving terms from the left to the right or from the right to the left. So we can't add, for example, 10 to both sides when we're verifying an identity. Or we can't subtract tangent x from both sides when we are verifying. We can only work with each side individually. We don't want to move things across the equal sign. So here's an example. Verify that the following equation is an identity. So we see cosecant squared x minus 1 divided by cotangent x equals cotangent x. And the strategy we are going to apply here is to work with only one side of the equation. So work with only one side of the equal sign. Okay, and so what we mean here by this strategy is, well, it's very tempting to say, let's multiply both sides by cotangent x to get rid of this fraction, because then that would cancel. Well, we don't cancel on the right side. This is very tempting, but because, again, we don't know that the left side actually does equal the right side, this is what we're trying to show. We can't just multiply both sides by cotangent x. So we don't want to do this. So we need a different procedure. And what we can see is that cosecant squared x minus 1, well, that is a version of the Pythagorean identity, or one of the Pythagorean identities. So cotangent squared x plus 1 equals cosecant squared x. If we subtract 1 from both sides here, and we can do this because we know that this is already a proven identity. So because it's a proven identity, we know the left side is equal to the right side. So here we can subtract 1 from both sides, and we get cotangent squared x equals cosecant squared x minus 1, and that's what we have in the numerator in our original problem. So what we can do is substitute cotangent squared x for the numerator. So cotangent squared x over cotangent x, and then from there we see that cotangent x and one of the cotangents in the numerator can factor out. So cotangent x equals cotangent x, and we got it. So when we're going through this process, the final step, we must show that the left side is explicitly equal to the right side. Okay? So if we had something like this, let's say we know that cotangent is cosine over sine, and if we leave our final step like this would not be completely correct because we have not shown that the left side is exactly like the right side. Now it may be obvious to you, but we must explicitly show that cotangent x is equal to cotangent x. That's the final step that we want to take here. All right, another example. Verify that the following is an identity. Secant theta minus cosine theta divided by sine theta equals sine theta over cosine theta. And the strategy we're going to employ here is we're going to change to sine and cosine. So all the functions we're going to write as in terms of sine and cosine. So secant is 1 over cosine minus cosine divided by sine theta, and that's just equal to sine theta over cosine theta. So everything is in terms of sine and cosine. Now what we want to do is in the numerator I want to add 1 over cosine, or subtract 1 over cosine minus cosine. And to do that, this is currently over 1, so I need to get a common denominator between those two fractions. And the common denominator is going to be cosine, so I need to multiply the second fraction by cosine over cosine. So what we end up with is 1 over cosine theta minus cosine squared theta over cosine theta, and that's still all over sine theta. I'm just working on the left-hand side right now. So each step as we go, we should write the equal sign vertically. So every step of the way, we should write a new equal sign. Now in the numerator, I can write this as 1 minus cosine squared theta over cosine theta divided by sine theta. Okay, I'm going to bring this up here. So what we have is, well, 1 minus cosine squared theta, we know that cosine squared theta plus sine squared theta is equal to 1. So sine squared theta is equal to 1 minus cosine squared theta. So what we're going to do is we will substitute sine squared theta in for this. So what we get is sine squared theta over cosine theta, all divided by sine theta, and that's still on the left side of the equal sign. And now from here we have a complex fraction. When we have a complex fraction, we multiply by the reciprocal of the denominator. So sine squared theta over cosine theta multiply by the reciprocal of sine. So the reciprocal of sine is 1 over sine. And then what we'll have from here is, well, this squared, one of those signs is going to cancel with this sign. So what we get is sine theta over cosine theta, and that's exactly what we have on the right. So sine theta over cosine theta. So the left side equals the right side, and we're done. So something to mention here is sometimes students, they get to this final step and they say, all right, we got it, and they put a box around that final answer. Now that's not totally correct here. Typically when we put a box around the final step, that's saying this is my answer. Well, actually this entire exercise, all the steps we took all the way down is the answer. So we don't really want to put our final answer in a box, because as I'm checking this, I'm gonna walk through every single step of the way. So remove the box if we put something like that. Moving on, let's verify this equation. Cotangent to the fourth x plus cotangent squared x equals cotangent squared x times cosecant squared x. So let's follow the same procedure as last time. Let's change everything to sine and cosine. So doing so, cotangent, well, that's cosine over sine. So this will be cosine to the fourth over sine to the fourth plus cotangent squared, that'll just be cos squared x over sine squared x. And then let's do the same thing on the right hand side. We'll have cosine squared x over sine squared x times cosecant squared, well, that's 1 over sine squared. Okay, let's see, on the left hand side, why don't we get a common denominator here? So I'm going to get one term, and the reason is because we have one term on the left hand, or on the right hand side, so let's get this down to one term on the left hand side. So to get a common denominator, I'm going to multiply both sides by sine squared, or rather the numerator and the denominator by sine squared. So on the left hand side we're going to get a common denominator of sine to the fourth, and then in the numerator we'll have cosine to the fourth x plus sine squared x cosine squared x. On the right hand side, just going to clean this up a little. We'll write this as cosine squared x over sine to the fourth. Now, looking pretty good here. We have the same denominator in the left-hand side and the right-hand side. On the left-hand side, what I'm going to do is, in each of these two terms, I have cosine squared x, so I'm going to factor that out. Cosine squared x. Cosine squared times cosine squared gives us the cosine to the fourth, plus sine squared in the numerator. Divide that all by sine, that should be to the fourth. And then hopefully what we see here is that this cosine squared plus sine squared is equal to 1. So cosine squared times 1 is just cosine squared divided by sine to the fourth x, and that gets us equal on both sides. So we have verified this. So looking at this problem, there are other ways we could have done this. We could have possibly used cotangent squared x. We could have possibly used a Pythagorean identity. When we see something squared, that's an option. And similarly, on the right-hand side, we have two trig functions getting squared. We could make a substitution using the Pythagorean identity, and maybe that would work. The idea here is that we need to try different strategies. Sometimes changing everything to sine and cosine will work. Sometimes it won't work. For this one, it worked right off the bat. So that's just something to keep in mind if you've never done these before. There's not necessarily only one way to go about verifying. All right, and then the last one in this section, we have cosine beta over 1 plus sine beta equal to 1 minus sine beta over cosine beta. Now again, resist the urge to cross multiply here. That is not something that we are able to do. So what we're going to do instead is I'm going to multiply both sides by the conjugate. Okay, and what is the conjugate? Well, what we're going to do is I'm going to multiply the top and bottom by 1 minus sine b on the left-hand side. And we're allowed to do this because 1 minus sine beta over 1 minus sine beta, well, that is just equal to 1, and we're allowed to multiply by 1 as much as we want. So on the left-hand side, when I multiply this out, cosine beta times 1 is cosine beta minus cosine beta sine beta. In the denominator, well, 1 plus sine beta times 1 minus sine beta, this is just going to be 1 plus sine beta minus sine beta minus sine beta squared. So those middle terms cancel and we end up with 1 minus sine squared beta. So 1 minus sine squared beta like this. And 1 minus sine squared, well, that is a form of the Pythagorean identity. So cosine squared plus sine squared is equal to 1. If we subtract sine squared over, we get cosine squared equals 1 minus sine squared. So this is equal to this. So cosine beta minus cosine beta sine beta divided by, instead of 1 minus sine squared beta, I'm going to write cosine squared beta. All right, and then in the numerator, I'm going to factor out a cosine, and we're left with 1 minus sine beta over cosine squared beta. And what we can see is that cosine with one of those cosines in the denominator is going to cancel. So what we are left with is 1 minus sine beta over cosine beta, and that is equal to the right-hand side. So we've got it.